Welcome back to Dave Does Math from Home. This is part 3 of our video series about rational expressions. Yeah, there you go, rational expressions. In part 1, we talked about what they were and how we were going to play with them. In part 2, we talked about multiplying and dividing. So now it's time to talk about adding and subtracting rational expressions. And this is sort of the more difficult operation to do with them. I think multiplication is a little easier. Adding and subtraction is a little bit more tricky because of common denominators. It's the bane of math students everywhere. If you want to add or subtract two fractions together, you need to make sure they have a common denominator. So sometimes for things like 2/3 plus 7/5, sometimes getting a common denominator is very easy. We need to 3 and 5 have nothing in common, so we need to multiply this by 5 over 5, and we need to multiply this by 3 over 3, so that the bottom for both of these becomes 15, and you get 10/15 plus 21/15, and then you add them together and you have 31/15, and all is well, and you don't have to really worry about this. Sometimes getting a common denominator is a little more tricky. If you have something like 13/12 plus 19/18, 12 and 18 have common pieces already. So you could still get a common denominator by multiplying them together. Like we could multiply this by 18 over 18, and we could multiply this by 12 over 12. I just don't want to do that. I don't know what 18 times 13 is off the top of my head. I don't know what 18 times 12 is. I don't know what 13 times 19 is. So I don't want to get a common denominator that way. To get the common denominator for this thing, I want to factor the denominators as much as possible. This 12 is going to be a 2 times a 2 times a 3. That's it factored down to its lowest pieces. And then 19... I don't care about the tops of these things. I'm only concerned about the bottoms. This is going to be a 2 times a 3 times a 3. So this is as factored as much as possible. 2 times 2 times 3 and 2 times 3 times 3. So if I want to get a common denominator here, this piece needs an extra 2 because they have the 2 and the 3 already. 2 and the 3 is what they both share from the start. This piece needs an extra 3. So now the common denominators are 2 and 2 and 3 and 3, 2 and 2 and 3 and 3. And that is going to make this a lot easier than trying to multiply the whole thing by 18/18 and 12/12. So this would give me 39 over 4 times 9 is 36. 39/36 plus 38/36. And if you add those together, you should get 77/36. Actually, I shouldn't have... Okay. So this is, I think, a pretty good quick refresher on fraction addition, subtraction, I guess, as well, using common denominators as a segue to doing it with rational expressions. The one thing that I feel like I did wrong in this example is that if I want to draw parallels between this and how I think we should do rational expressions, it would be we don't need to simplify the bottom right away. So when we're doing this with rational expressions, I would encourage you to keep the bottom factored as long as possible, because sometimes when you add the pieces of the top together, you end up with things that might cancel on the bottom. So let's see what I mean by that. Let me do an example right away where that happens. let's look at 8 over x squared minus 16 plus, minus 5 over x squared plus 3x minus 4. So, as with every other problem we've done in the rational expression section, our first priority should be factoring everything as much as possible. So when we factor this, we'll get 8 over x plus 4 and x minus 4. And this will be 5 over x plus 4 and x minus 1. So right away we can hit our domain restrictions. We can get our x can't be -4, it can't be +4, and it can't be 1. These are our 3 domain restrictions. So the reason that we're factoring this, hopefully this is clear from the 13/12 example I just did with actual numbers, is that instead of getting a common denominator by multiplying these two things together and getting some absurd 4th degree polynomial that no one wants to deal with, we can, if these become factored, we can see that they already both have the x plus 4 piece, and I don't need to repeat that. All I need to do to get these things a common denominator is I need to get the x minus 1 in here. X minus 1, x minus 1. So I need the x minus 1 over here so that this has all 3 pieces. And I need the, here we go, the x minus 4 here. So adding just one piece to each of these is a much easier process than trying to multiply these two entire polynomials together. This is why we always, always, always factor first. So I'm going to leave the bottom of this unfactored. So the bottom is going to be x minus 1, x plus 4, and x minus 4. I'm just going to leave it like that. This piece on top is going to be 8x minus 8 minus, this has the same denominator. Don't need to worry about that. This is just my shorthand. I'm not going to write all this again. It's the same. We know it's the same. We made it the same. So we're going to subtract 5x minus 20. Here's an interesting thing to keep in mind about subtracting. You have to subtract the whole thing. So we're subtracting 5x. Sure, and when we do our 8x minus 5x, we're going to get a 3x. That's fine. But we are subtracting -20, which is sort of the same as adding 20. So when we do our -8 plus 20, we're going to get a 12x back here. Not 12x, just 12. No x's in that one. So once you have your common denominator, you're combining like terms across the top, just like you always have been when you add polynomials or rational expressions together. And then the bottom stays the same. X minus 1, x plus 4, and x minus 4. So the reason I'm keeping the bottom factored like this, you can sort of see my head from down here, that's fine. The reason I'm keeping the bottom factored like this is because there might be more to do after you add things. And in this problem there is. 3x plus 12 is the same as 3 times x plus 4. So we still need to cancel some stuff. The x plus 4 and the x plus 4 cancel. And your final answer should be 3 over x minus 1 times x minus 4. But these domain restrictions stay. So this was kind of like a throw into the deep end example where every possible little weird nuance happened. The good news is they're not all going to be like this. Most of the examples we do of adding and subtracting things will be a lot less involved. This is just a comprehensive example of everything that could possibly go wrong happening all in one problem. We had quadratics for both denominators that we had to factor, and we had one matching piece, so we needed to get the other piece in there, so we had a 3-factor denominator. And then we had subtraction, we had to remember how to do that. And then we had to factor the top so that we canceled with the part of the bottom. So that is the whole deal. Let's do another example that is slightly less crazy. Probably should have started with that one and then gone to this one second, but hindsight. Okay, let's do something like 4 over x plus 4 plus x squared minus 5x plus 6 over, we'll do x squared plus 5x plus 4. So, as always, we want to start by factoring things. This is already as simple as it gets, so no need to factor that. It's just 4 over x plus 4. Here's what's weird about adding and subtracting. Don't mess with the tops at all until the very end. Like, we could factor this top piece here. It would be x minus 2 and x minus 3, but we shouldn't. We're not multiplying it yet. Just leave it alone. X squared minus 5x plus 6. At the start of these addition and subtraction problems, only worry about the bottoms. Completely ignore the tops of everything. Just factor the bottoms to get your common denominator. This is going to factor into positive 4 and positive 1. So we have a matching bit. We can use that to get our common denominator. All we need is for this to get an x plus 1 and an x plus 1. So we'll toss that in there. This is going to turn into a 4x plus 4 over x plus 4 and x plus 1. Oh, let's not, before we change too much, let's not forget about our domain restrictions. X can't be negative 4 and negative 1. We'll keep those handy. This part doesn't need to change at all. That's just our x squared minus 5x plus 6. That's why we didn't want to mess with the top, because if we'd factored it, we would have had to just unfactor it right here to add it together. And there's no point in doing extra work if we can avoid doing extra work. So we have a common denominator. We can just add straight across the top. The result will be denominator unchanged, still x plus 4, x plus 1. We need to combine some like terms across the top, so we'll have an x squared. We'll have a 4 minus 5 is minus x. 4 plus 6 is plus 10. And now we should check the new top polynomial might factor, and if it does, it might cancel with something on the bottom. So we need to check if that's the case. It looks like that's definitely not the case here. The only thing 10 could factor into is 2's and 5's, and that's not going to get us a -1. So there's no way to factor the top. We're just going to leave this as is, and the domain restrictions are still -4, -1. So this is probably the example I should have led with. It's a lot more tame. It's a lot more reasonable. There's less crazy shenanigans going on. I think I just got really excited about explaining from the fraction example. I got really enthusiastic about explaining why leaving the denominator factored was wise. Just wanted to show you why right away. Next time I make a video about this, I'll remember. That's about all I wanted to say for adding and subtracting rational expressions. You factor the bottoms of things. Don't worry about the tops. Just factor the bottoms of things. Get your common denominator. Like, take advantage of whatever repeat factors you have across the bottom to get your common denominator as easily as possible. Then add straight across the top. And then at the end, or subtract the entire thing. If it's subtraction, remember you have to subtract all those pieces. It'll help to distribute that negative sign to all those things, just like when we were subtracting polynomials. And then in the end, see if the top factors. If it does, see if anything cancels. Don't forget your domain restrictions. That's the whole thing, adding and subtracting rational expressions. And we've already done adding and subtracting, or multiplying and dividing rational expressions. And we've already done simplifying rational expressions. So that's it. That's the end of section P6. Stay tuned for some more videos. We'll get section 1.2a up and running right away.